Hey, Mike here. So I'm working with the fridge. I'm always working with the fridge. I've just been observing it here in the last couple of weeks. We've put it in. I have put it in the lab here. I keep the place warm with this small space heater that's hooked up to a thermostat. Keeps the temperature stable at right around 70 degrees. Obviously, it runs more when it's colder outside, but it's very good and it's more than enough. I run it on the low setting, which is about 750 watts, which is way more than it really needs. 300 watts would probably be a little bit better. I want to put a heat pump in, and I just need to get around to it. I've just been lazy and it's crappy outside, so I'm going to run out of winter soon. I better get it done. So I'm going to be building a new refrigerator, new chilling module, and I'm going to do it from the ground up. I'm going to completely rebuild the whole thing and kind of use what I've learned in the last several months and design something that should work better. It'll look a lot better. It'll be easier to work on. Something that's much closer to what I imagine the eventual chilling module will look like. So before I do that, I figured I might as well use this opportunity with the model I already have that works relatively well and maintains the temperature in the cabinet right between 33 and 37 degrees very consistently. The total cycle is about 6 hours. 2 on, 4 off, 2 on, 4 off. It's pretty much like clockwork. So there's a couple of things that I could do to tweak this thing. There's a lot of things I could do, and I just thought I would go over some of my thoughts on how I could go about that. So if I'm trying to improve the characteristics of this thing, essentially I want it to be I want it to use less energy in the long run. Efficiency is not my number one goal. Efficiency is important, but I want something that's rugged and robust, that works rather well. And because I will be switching over to a DC compressor, like this one sitting on the floor, this little Danfoss that a very, very nice friend from Texas sent my way. The idea is eventually it could be for kind of a solar, wind, off-grid type setup where you have batteries, and I'd like it to be able to keep cold for several hours without having to run. So one of the first things that people that get into this kind of stuff jump at is the compressor. Well, I need a more efficient compressor. Need a better compressor. Need a better compressor. Well, better compressors are great, and they have their use. But if you have a lousy design system, better compressor is not going to do you any good. It's a waste of money. So you need to design a good system first. So that's why this compressor was just ripped out of a refrigerator. It's just about as good as any other compressor as far as I'm concerned. And it serves my purposes well to try to improve the performance before I look into what kind of compressor that I ultimately want to use. The next thing, and the simple thing, is to just have a better cabinet, just more insulation. This thing is just a standard refrigerator. It's probably about 1.25 inches of insulation there in the bottom, and a bit more there between what used to be the freezer section. Pretty decent door. It's a lot better than the little mini fridge that I had. A better cabinet is an obvious solution, and eventually I'm going to build a really well insulated cabinet. But the focus is on the module itself. So I can look at better heat exchangers to be able to dissipate heat at a lower temperature. I can look at the capillary tube, the length of it, the bore of it, the heat interchanger that wrap around right there. I can look at the evaporator. That's a big focus. This evaporator here is a 2-inch half stainless steel steam table pan for a restaurant. It has a propylene glycol and water in it, and that non-eutectic mixture freezes at a temperature lower than the normal freezing point of water. And what that allows me to do is, with the evaporator coil that's in there, there's a 1/4 inch length of tubing coiled up inside the bottom of that pan. During the run cycle, it can freeze that mass, and then during the off cycle, the fins on the evaporator glycol pan can absorb heat from the cabinet, keep it cool, and of course the fan can assist in that as well. That's something I added a couple of days ago, just kind of as a goof, because there is some interest in adding a fan to the model I'm going to be building. And so far what I've seen, I think it's going to be a wise choice. I don't want to be reliant on fans. I want to be able to design a system that can operate essentially statically, where the only moving part is the compressor itself. But integrating fans into it is still an interest of mine, and sticking to kind of a standard low power BLDC, something that's easy to come across in case it ever fails, easy to replace, might have its application. So the condenser itself. This condenser, there's a number of videos talking about the creation of it and the impetus for building it. It's worked out rather well. Things that I could do to improve the way that this one's built: it's just about 50 feet of 1/4 inch tubing. This thing should have been 3/16 tubing. I got a number of reasons why. 3/16 is going to have more surface area per unit of volume relative to the unit of volume, rather than 1/4 inch. There's less volume inside the tubing. Essentially, I can get up to those higher pressures and have more of the refrigerant exposed to the walls of the tubing. That's the overview of it. There's a lot of other reasons for it, but anyway, it ended up being 1/4 inch for that's what I had on hand. So I could also paint this whole thing black. It should be painted black. It was intended to eventually be painted black. I just never got around to it. I probably still won't get around to it. That would probably dissipate heat a little bit more effectively. I could add more surface area to it. You can see these holes here were actually intended to add skin to the outside and the inside, and I determined that that wasn't going to work all that well. I was going to add some bands to this, but I'm not too worried about it right now. The fan down here does blow some air across the bottom and adds a little bit of subcooling, and a fair amount of subcooling. It will run without the fan. It just runs a little bit longer and a little bit hotter. So that's where I stand right there with that. The capillary tube. I've had some thoughts about shortening it in the last couple of days, but I'm not jumping into shortening cap tube. Once you shorten it, you can't re-lengthen it. So 10 feet has served me well so far. If anything, what I'll probably do, I'm going to have to pull the charge out to do this, but I'd like to decrease the amount of my heat interchanger there. The capillary tube wrapped around the suction line. It's probably about 3 feet of the total 10 feet wrapped around that. I think I went a little overkill on that. Probably maybe a foot would have been more than, plenty. That's going to be kind of difficult to unwrap it. It's going to be pretty ugly. So reasons for that. When you wrap cap tube at a really tight radius like that, any tubing at a tight radius, it creates some extra restriction. So it's no longer just simply 10 feet of capillary tubing. There's 3 feet of tightly wound cap tube, so there's probably some extra friction created by that. The main reason that I think 3 feet is too much is there's too much heat being added to the suction line. And when all that heat gets added to the suction line, the temperature of the suction vapor going back to the compressor is higher. It's not going to cool the compressor as effectively. And the worst thing about that is that the density of that gas returning to the compressor is a lot less. It's a more rarefied gas. So for every stroke of the compressor, there's less mass flow through it. If there's less mass flow, it's less efficient compression. There's more wasted heat. There's more discharge superheat, which is more heat that needs to be dissipated. And with less mass flow through the compressor, we have less efficient compression, so we're not moving as much mass into the high side as we would like to. That's especially a concern at the beginning of the run, whenever we don't have a liquid plug at the inlet of the cap tube. We're just pushing hot gas through it, and which creates a lot of gas doesn't like to flow through a cap tube very well, and eventually we get that pressure differential between the high and the low side sufficiently large enough that in the high side the vapor begins to condense as the temperature of the copper starts to rise. And once we get that liquid plug on there, we start to get liquid being fed through to the low side. Once liquid's fed through the low side, then we can get a little better cooling. We can supply the evaporator with more liquid such that it will return a denser gas, denser vapor back to the compressor, which then results in less, more efficient compression and more mass flow through the compressor and more mass flow through the condenser, more mass flow throughout. So we want to get to the conditions where we get that good liquid plug on the cap tube. Now, also, if I'm not getting that really good subcooling, I still have a lot of heat left at the cap tube and at the outlet of the cap tube. So if I don't use the heat interchanger, I'm not bypassing the evaporator with that heat like I am with the interchanger. It's flashing in the evaporator itself. You're always going to have some of that. I just think that this is it's a bit overkill. I might have a suction temperature after the evaporator of 0 degrees Fahrenheit, let's say, and then coming back to the compressor, it might be 40. It's a lot of suction superheat. It's excessive. I don't have any insulation on here right now. It's a bit of laziness on my part, so that's obviously not helping either. But I've had enough experience with this heat interchanger to know that I think it's a bit much there. So there's a couple of other things, the way that the tubing is run and things, but those are mostly minor issues. Going into the inside of the cabinet, this is where things get really interesting. So I'm going to be making a completely new evaporator. It's going to be a different style of pan. It's going to be round. It's going to have TIG welded fins. The fins probably aren't going to be as long. You can see the ice formation against the pan, and that stays pretty well constant. It gets to a certain thickness, and it pretty well just stays there, which is kind of nifty. So not really getting any heat exchange air to the metal there, obviously because of all the insulative ice. But with these fins never really frost up. So even though it's stainless steel and it doesn't have great thermal conductivity, it does obviously absorb some heat and transfer it into the bottom of the pan. So fins are very important. The fan itself isn't crucial. I found that once I installed the fan, I could run the thermostat at a slightly larger range of temperatures and a higher range of temperatures. Say before, I might want to run it up to about, 25, 26 degrees. That is the temperature of the bottom of the pan, against the ice. With the fan, I can run it up to about, I think it's at about 34 right now. So that allows the air temperature to get as high as 37 in the cabinet. And then the low end of the thermostat's about 16, which at the end of the run cycle is about 33 degrees. So I want to toy with that a lot more, and I want to improve that range. I want to use the ice that's storing all that cooling load or cooling power as effectively as I can. I want to use as much of the mass of ice. I want it all to melt, as much of it to melt as possible till the end of the run cycle, and then completely refreeze it. That is a kind of a difficult problem to address. I can't really go into all of it here on a video, but a lot of what it comes down to is you have to have some balance between the distance between the evaporator coil itself that's in that pan to the pan surface itself, and then you have to think about how much ice is going to be between that coil and the pan, how much ice is going to be between that coil and another part of the coil, because once that ice begins to form, the amount of thermal transfer of heat into the coil to cause the evaporation inside of the evaporator coil, that starts to decrease. So it becomes more and more difficult to extract heat out of there effectively. And one of the other issues with that is from the beginning of a run cycle, when most of that liquid or most of that substance is a liquid, where it transfers heat somewhat effectively, till the end of it, till it's almost all ice, the evaporator has very different characteristics because of the amount of heat that it can be absorbed through the evaporator has decreased so much once the ice is formed, that a certain amount of liquid being fed into it at the beginning might not be enough, but by the end it's almost too much, because it's not volatile enough to vaporize away. So it becomes kind of important to have some kind of an accumulator on top. The fan also keeps the air from stratifying too much, keeps the temperature more or less stable, consistent throughout the whole thing. can already see with the door open we're melting a little bit. So it's going to be a little goofy run cycle here, and it's not going to be as consistent as the rest of them here. So why don't I show you what the last day or so has looked like yourself. So what you're looking at here is about 21 hours because of the way that this goofy software works. We have 30-second intervals between samples, and so 21 hours across here, approximately 4 hours between each one of these vertical lines. Okay? Each one of these kind of lobes here should be obviously a run cycle, and then the long stretch in between is an off cycle. So about 2 hours run, about 4 hours off, 2 hours run, 4 hours off. You see that they're relatively consistent. The shape of all of them, everything is really, really consistent. It's kind of crazy to see it, and it's crazy to see how small, minor changes can affect the way that the system performs. Let me take a little sip. What do we got? Blue Moon Cappuccino Oatmeal Stout. Not bad. Bought a few of them. So I'm not going to go into too much detail here. The software's been updated recently. Zoombox released a newer version of the software. It allowed me to change the colors and actually label the inputs, which is nice. But there's a few more things I would love to see on this software. We have discharge superheat, subcooling. We have 2 ambient temperatures, including the Zoombox internal temperature itself. We have a superheat after the evaporator, superheat after the heat interchanger, which is noticeably higher. We have that green line that comes across, which is the cabinet temperature, which you can see just goes up and down rather gradually, because remember this is 21 hours, so it doesn't vary too much. The brown line is actually the temperature in the pan. Then we have this black line that comes up and down. Those are actually, that's the pressure, that's the head pressure. So you can see a very sharp rise and a very sharp fall off there when it starts and stops. And then there's a much lighter line that's below it, which represents the suction pressure. So like I was talking about before, I generally want to increase the off cycle, and I can do that by adding insulation. I can decrease the run cycle by adding insulation too, because remember, each time this thing runs, say when it runs right here, it has to dissipate not only the heat of the compressor, but also the heat that's absorbed by the refrigerator cabinet during those 2 hours, and the heat that was absorbed by the ice, which was the stored cooling power from the previous cycle, has to absorb or dissipate all of that heat that was absorbed by the ice during that 2 hours. So by adding a lot of insulation, we can decrease the amount of heat that was absorbed during the off cycle and increase the length of that off cycle. We can also decrease the amount of the run cycle. And that's not exactly true, because if we're increasing the off cycle, but you get what I'm saying, is that what we're trying to do is decrease the amount that it runs, and the amount of time that it runs and how often it runs. So if I'm trying to increase that off cycle without really fooling around with the insulation too much, I have to look at using as much of the cooling capacity of the ice as possible. Now I know I'm not using all the ice. Hell, I doubt I'm using 50% of the ice that I have right now. So I have to design a better heat exchanger and find ways to use as much of the core of that ice as I can and make sure that I can melt as much of it as I can. And then when it comes time to refreeze it, to freeze it effectively. Not in such a way that there's a very thick block of ice in it, and the evaporator has to get very, 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 very cold to refreeze that liquid that's, several centimeters away from the tubing. So I do that with various, fin configurations and things like that. So that's kind of where I'm at right now. I'd love to go into talking about the next design. But it's not going to make a lot of sense because it's all kind of just in my noodle right now. But it'll have some similarities to this. I mean, it's going to be round, but it's pretty much all going to be round. Everything about it, the base is going to be round, the control panel, everything. It's going to all be more or less concentric, and the evaporator too is all going to be round, and the fan's probably going to be mounted in the bottom blowing upwards. There should be a condensate pan. it'll be a much nicer machine. So I don't really know what else to say right now about it. I just thought, you know, I've been pretty absent in terms of this machine because of the winter, and I'm ready to get back to work. So a couple of tools that I bought should really help me out with that. So thanks for watching.